Whew. Look at that one. That's a pretty hard example if you ask me. But I imagine if you saw this on your exam, you'd just be like, oh, I don't know how to do any of that. Well, nonetheless though, thank goodness I'm here to actually go and help you out on this kind of a problem. So let's begin. Let's actually start with understanding that we have two different guys multiplied together. We have e raised to the negative x cubed times an x squared. Now, a couple things need to come into mind. Of course, when we deal with any sort of e raised to an exponent, that of course is going to be our exponential rule. And sometimes actually, I think it might be very helpful here if we actually remember the rule for the derivative instead of the rule for the integral. Why is that, you might ask? Well, as you might see here, that this is our note that we're going to make to the side, is that we have e raised to the negative x cubed. Now this guy though, because we have an exponent raised to another exponent, what a world we live in, huh? But nonetheless though, with such a way that they wrote out this problem, is that we're going to have the negative x cubed and an x squared. They need to have some sort of relationship to each other. What could it possibly be? Well, now that's where that note comes in, because if we go forwards first, that it's e raised to the u, we take that derivative. The derivative of that exponent will have to show up at a later time. Remember, this note here for our derivatives is a good way to remind us what our answer needs to look like. Always remember is that with every single one of our answers coming off of an integral, we will check back with a derivative to make sure that we are on the right track. So why don't we go ahead and do that? Because if we take a look here, the negative x cubed, this guy, that exponent in this problem, that guy's derivative is going to be negative 3x squared. Obviously with some power rule going on over there. Well, what would you know? That we have something that matches quite similar to what we have over there as that coefficient. So I think we're getting somewhere. So why don't we just take it to the next logical step of simply trying something out. And that's the best part about these integrals, is that if you have an idea, you can try it out and you can go ahead and take its derivative. So starting here, we have e raised to the negative x cubed. This guy needs to be obviously in the answer, because any sort of e raised to the exponent, it's going to match through and through from the derivative. So this guy needs to show up. So let's just say for our own amusement here, we can just leave it like that. E raised to the negative x cubed plus c. Now, of course, is that a right answer? Well, now it's time that we go and take its derivative just to see how close we really are to that answer. So if we were to go and grab this entirety of our proposed answer and take the derivative in respect to x, we would then achieve the following. Of course, e raised to the negative x cubed will leave itself exactly the way that it is, except now we have chain rule, because that exponent, the negative x to the third power, that must also have its derivative taken, and then of course the plus c goes to a 0 from the derivative. All right. Well, looks like we're on some sort of track. Is it the right one? I don't know. As they might always say, we might be going places, maybe not college, but places. So let's keep going here. So the e raised to the negative x cubed is still going to be the same. But now, of course, that second note does help us right there, because it looks like we are indeed taking the derivative of negative x to the third power thanks to chain rule. So we have negative 3x squared coming out. Oh, would you look at that? We are quite close. If we were to clean this up just a little bit further, we are indeed very close to what we started with. We simply have a negative 3, but all of this we do like very much. This looks like pretty good business to me. It's just that that negative 3 should not be there. But like I said, everything else looks pretty good. So what can we do to make sure that negative 3 is no longer there and we can end up with an answer, not exactly this, but a better proposed answer that will lead to exactly what we started with? Who would have guessed that that is just a coefficient? We simply need to now state that if we take negative 1/3, that will multiply with that negative 3 and cancel out and give us that positive x squared that we like. And would you look at that, we would end up with this proposed answer instead. So again, we're making a little bit of a separation here between a tested answer and then the new proposed answer. So let's clean this up here, because negative 1/3 multiplied by a constant is going to be still that same constant that we haven't solved for yet. So we end up with negative 1/3 times e raised to the negative x to the third power. Well, with that plus c added to the end of that, again, this is our next proposed answer. So why don't we go and check that again? We could only circle answers once we have absolute certainty that our work has ended the way that we want it to. So let's put this together. So we end up with the negative 1/3 as a coefficient from the derivative. We'll leave that alone, that's fine. E raised to the negative x cubed power. And then of course the same exact chain rule will follow after taking that derivative. So it's negative 3x squared. And of course the plus c goes to 0 as always.
There you go.
It looks like we finally have canceled out that negative 1/3 with that negative 3 that we liked. That all goes to a positive 1. And so this results in e to the negative x to the third power times the x squared by cleaning it up a little bit. And then the plus 0, of course, with the c. That doesn't matter, because what matters now is that we have matched this 100% with our starting answer inside of the integral. Okay, now that we checked everything off, it looks like indeed this proposed answer we had on the second time around has indeed made it through properly. We end up with the negative 1/3 e raised to the x cubed plus c. Now that is how you integrate that guy right there. Not too bad for something that just takes just a few iterations through, but this is indeed a surefire way to make sure that we've been checking all of our steps to make sure we end up with the proper answer, that even with our little extra steps here to ensure that we are on the right track, looks like this is not too hard of a problem to solve for. Let's get to the next one. Ooh,
What is it?
This is a great, I would say, transition from using just only e to the x, now with a number raised to the x power, the exponential rule taken for simple numbers. Well, this guy is also a real doozy, but again, our ideas still hold the same about how to implement the rules that we've learned earlier, such that we can solve for these types of integrals. Now, as before, I usually like to make a couple of notes onto the side for myself to make sure that I know exactly which kind of rules or which ideas need to be applied to this kind of problem. So starting out with, we got that 4 raised to the x power. 4 raised to the x? Always remember that 4 raised to the x, if we were to run that kind of integral just on our side here, we can now recall back to what the exponential rules would apply for integration. So remember that. Similar to e raised to the x, remember e is simply just a number as well, just a nice long and irrational number. But nonetheless though, that idea still is going to apply, that 4 raised to the x will result from the integral. But now we have something else coming along here, is that we have the natural log of 4 on that denominator coming out. And of course that plus c. Why is that? Well, if we were actually paying attention to the previous lecture, or if you just simply forgot, is that going the other way though, taking the derivative of 4 raised to the x power, it will result in the same 4 raised to the x power, but now instead we're going to be multiplied by the natural log of 4. So again, these two are two separate ideas that are coming together inside of this integral. Normally, this will not apply for e raised to the x power, as what we will normally see very often in calculus, is because, of course, that last bit, the natural log of the base of the exponent of e will always just turn into 1. How very convenient for the natural log in e to be in such a great relationship, while for any other number as the base for these exponents, it's not so much. But still, this note here will be something that's very helpful to us that hopefully we can start to see come about. Now we have the next issue. We have a tangent. Oh dear. Tangents were so easy to take derivatives of, but how in the world are we going to go ahead and take the integral of tangent? What if, oh no, we forgot how to do these types of integrals? Although I clearly did say on a different lecture about what that integral was, let's just say, for example, you had no clue. How then could we do this part? Because this part is going to be a very big important factor in this kind of problem. Well, who knows? Perhaps you have absolutely no idea how to do that. Well, we're going to have to take this one step at a time, won't we? Just always remember is that we can always break up, especially for anything with tangent or usually any other trig function, you can always break it up to its easiest components of sine and cosine, because hopefully you should know how to deal with those kinds of integrals. Of course, the sine and cosine relationship being very nice, very nice, over how they can easily transition from one to the other, thanks to the sine deriving into cosine, of course, cosine deriving back to negative sine. And so with something like this, if we understood our chain rule well enough, is that all we really need to know is that it's a natural log of cosine plus c. But then, of course, with the cosine business going in the derivative, we will need a negative on the outside of that. Why, of course, is that we need to shove a cosine in the denominator while we leave a positive sign in the numerator. This is how it's done. That's the good stuff right there. By being able to focus on having this as a result, that is one way of doing it. But of course, let's say instead you were more in the lines of course I know integral of tangent, brother. It's not so hard. It's just supposed to be the natural log of secant of x with a positive sign. Woo! Don't I get a cookie now? I'm so good at calculus. Yeah, sure. If you remember this, that's wonderful, right? You were able to keep the positive sign, blah, blah, blah. Good, you memorized something off a book, whatever. Let's get to the problem now. So, going over here, we have a tangent of 4 raised to the x power, and we still have another 4 to the x power on the outside. That is actually quite helpful to us. Again, with our note, understanding that even after we take the integral of the tangent, we still need to keep in mind for the resulting 4x inside of it. Remember, when we think about every single one of our answers, we need to understand that chain rule will come out whenever we take the derivative of our proposed answers. So same idea here. Why don't we go ahead and take a first jab at this and see if an idea can prop up. So if we were to just take the integral of just the tangent of 4 raised to the x power, instead we're going to look at focus on just that. So that resulting integral, just to show you that we are keeping up with our first proposed answer, is that instead of just calling it tangent to the 4 raised to the x power, let's go ahead and run one of our proposed notes here. Is that we will call it the negative natural log of the absolute value of cosine of 4 raised to the x power, all of that plus c. That's not too bad. Now, of course, we're not just going to leave this alone and say, oh, we got this. All right, see you all later. Absolutely not. No. We have a lot to work on still to understand that we have to check this guy with the derivative to make sure we lined everything up. Oh, but what do I have to check? It's such a waste of time. Pay attention here. We're supposed to be making sure that all of our answers do match up. Why would I be here if I'm not going to make sure that all of our students are going to be able to provide us with the right answers? All right. So let's get on with the check. The negative natural log of cosine of 4 raised to the x power, that instead will give us a negative 1 over the cosine of 4 raised to the x power. And now we need to peel this onion back one layer at a time with chain rule. We did the natural log rule. That's pretty good by sending that cosine into the denominator. Now we got to do the cosine rule, which is going to be the negative sine of 4 to the x power. And then after that, we have one more layer to peel back. We have 4 raised to the x power, that rule, which will then be 4 raised to the x power times the natural log of 4. And would you look at that? We have all these layers that we need to keep track of. And so let's just clean this up just a little bit more. We have the negatives canceling out, thankfully, because there's 2 of them. And so we have sine to the 4 raised to the x power over a cosine raised to the 4x power. And then we have 4 raised to the x times the natural log of 4. We were almost there. This, of course, sine over cosine, giving us tangent, and then 4 raised to the x, matching exactly that. But this, what's up with that? And that, of course, is why we should have paid more attention to our starting note up here from the very beginning. We were supposed to throw down a natural log over 4 to cancel out with this. But shouldn't there be chain rule? I think you're forgetting something. This is simply a number. The natural log of 4 is a way to rewrite an exponent using a logarithm. This is just a number, or in other words, for us, a coefficient. So let's try one more time, but why don't we spice it up a little bit? Why won't we use this rule instead, the natural log of secant of x plus c? We can do just that. So let's skip on down to our second proposed answer instead, and let's have a look here. So that integral instead will lead us to the natural log of secant of 4 raised to the x power. All of that. Now we need to multiply. We have one more issue here to deal with, is that natural log of 4 in the denominator. So 1 over the natural log of 4 as a way to cancel out with the outgoing chain rule product. And then lastly, we have a plus c at the end. So why don't we check this instead with a different look on the tangent integral, but hopefully, again, as always, all of this will match exactly what we started with. So let's take a look here. We'll take the 1 over the secant raised to the 4 to the x power. That's the first step, so we check off the natural log. Next, we have secant. Secant? Oh dear, are we forgetting something? If only we can remember our derivative rules of taking the derivative of secant. Now, I would absolutely love to go over all of them with you, but I don't have the time for that, and neither do you have the attention span to hold on to some of that information. It will be up to you to remember that this is the result, tangent times secant for the derivative of secant. So that's good. That's the secant business taken care of. Now, of course, we need the 4 raised to the x power taken care of. Then that derivative is 4 raised to the x, again multiplied once more by the natural log of 4. So that is all of this derivative. Isn't that just wonderful? All of that came out of there. And now we must continue with the rest of our proposed answer. We still have that 1 over the natural log of 4 to maintain. And of course, that plus c goes to 0 from the derivative. Oh man, looks like there is a lot to clean up, but also a lot to cancel. The natural log of 4 of there being canceled with the natural log of 4 down there. And would you look at that, we have a secant over there canceling with a secant over there, all of 4 raised to the x power. So all that we're left with are just a few things in O. It looks like we finally figured it all out. We indeed end up with exactly 4 raised to the x power times tangent of 4 raised to the x power. And we've matched it all exactly with what we started with. So, if you imagine that, this was indeed the correct answer to our integral. But why don't we clean this up one more time just to make sure that everyone can see this properly? That what we put down instead is that it is a natural log of the absolute value of secant of x, well, not really x, let's try that again, of 4 raised to the x power, that's what it should have been inside of the function, and all of that raised over the natural log of 4 as a way to cancel out the 4 raised to the x when you take that derivative, plus c at the end of that. And there you have it. A nice clean answer to a nice clean problem. Don't we feel so much better now that we can do these types of derivatives? All it really takes is for us to go step by step, run some ideas that we need to remember from all of our previous lectures, and to really try to put some ideas together, and of course, checking our way through at the end of it. It really isn't that hard of an issue, it just really is a matter of time and perseverance for many students. Seems pretty good. So, to really wrap it all up, we only have, I would say, 2 more lectures to deal with here, and then we'll be home free to now be dealing with some more problems on Wednesday. I'll see you then.